I suspect that several of you are summer school students and some of you are refresher course participants. So I hope that the talk and the lecture is actually at the level that both groups will sort of benefit from the talk. Now, I think I have one request, so we'll definitely take questions at the end. But if there is a pressing question and at any point of the lecture, at any point of time during the lecture, you think that you need a clarification or something's unclear, uh, yeah, please you can unmute yourself or type a question in the chat box if there is something like that, and then at the end we'll definitely take questions. Just in case there is some short clarification question, please feel free to stop me, okay? Because I tried to keep the talk sort of at a pedagogical level, so that's why the interaction is probably very important. And I'm greatly thankful to IUCAA for giving me this opportunity to talk to you. And my name is Chatterjee, and I am an assistant professor at the Department of Physics at Presidency University. And so my expertise, I work on cosmology. So is astrophysics, several problems on astrophysics and cosmology related to active galactic nuclei and their cosmological implications. And what I'm going to talk today, so I'll just stop my video if you don't mind. So what I'm going to talk today is, if you have seen uh, the booklet or the schedule, it's about the anisotropies in the cosmic microwave background. Okay, so I'm going to use slides, and at some parts I'm going to also use a whiteboard where I'll do some little bit calculations to make my points. Okay, so let's start. So first I'm going to tell you what this cosmic microwave background is and what kind of anisotropies are we talking in this context. So let's see. Okay, so here is a cartoon picture, but it's a very beautiful picture of the evolutionary history of the universe, and this is from the WMAP team. And you must have heard, at least definitely some of you must have heard, that the prevailing theory in cosmology about the evolution of the universe is the Big Bang theory, where the universe started. So universe has a finite past, so it started from the Big Bang and then gradually as an infinitely hot dense phase, and then it gradually expanded and cooled off. So here is actually a brief timeline, and roughly the age of the universe has been estimated to be 13.7 billion years. I shouldn't say roughly, because this number is kind of quite precise, but yes, it's around 13.7 to 14 billion years is the age of the universe. Okay, so we have been it's been 14 billion years since the Big Bang. Now here is the brief timeline. So you have some epoch called the inflationary epoch. We have quantum fluctuations at that time. This is the picture that will come again and again during our talk, because this is the epoch of the cosmic microwave background, and we'll try to briefly understand the physics of the cosmic microwave background and what can we do from it. Then we have a universe when it was neutral, and we call it dark phase, dark ages. This is currently a very, very important epoch of the universe, and lots of observations involving the 21 centimeter hydrogen line is being utilized to understand this dark phase of the universe. And then we have the formation of the first stars. So now you have again radiating objects formed in the universe, and then the stars. There are many stars, and then galaxies form. Galaxies, quasars, very, very, very bright objects which have central supermassive black holes, and the universe gradually expanded, and we have structure formation. Now, one important thing that happened during the epoch of the during this expansion of the universe is that the universe initially was decelerating. Okay, so it was expanding, but the rate of expansion was slowing down. But then about redshift 1 or a little bit after, so it's in the recent universe, redshift 1-ish, or after redshift 1, the universe showed evidence of accelerated expansion. And that's the important thing that you might have heard during the summer school. That is the dark energy accelerated expansion phase. And we are still in this dark energy dominated phase of the universe where it's where it's actually accelerating. How it's accelerating? We have to figure out. Right now, we believe that it's exponentially accelerating. But this is a brief timeline of the universe. So today, we are going to talk about the phase of the universe when the universe was roughly 400,000 years old. So it's a very early phase of the universe. And it is exciting to learn that we have tools today. Currently, this is the WMAP satellite, which is a very, very famous CMB. We call it Cosmic Microwave Background Satellite Experiment that gave us wealth of data with which we can use the information from the cosmic microwave background and study this phase of the universe when it was very young, very hot, and very smooth. Okay, so that's what we're going to talk about. So what is this cosmic microwave background? Now, this is a very, very big confirmation of Big Bang cosmology. It was first when the Big Bang theory came into picture, from in the early 1920s, Lemaitre and others sort of spoke about this Big Bang expansion, and this Big Bang issue, because Hubble's law was discovered, which told us that distant galaxies are moving far away from us, and that gave, when you extrapolate that idea, that gave the idea of a Big Bang. That means a point in time in the history of the universe. So that essentially gave us the idea of a finite age of the universe. Now, from this Big Bang proposition, George Gamow in the 1940s predicted that there will be a background black body radiation which will be signature of this hot, dense phase of the universe. So this was a prediction in the 40s, but it was not detected at that time. So these black bodies, a relic radiation from the Big Bang, a signature of its smaller, hotter, denser phase of the universe. And then it was not discovered, but then almost accidentally, we'll not get into the story, but it was accidentally discovered in the 1960s by these two radio astronomers, Arno Penzias and Bob Wilson, and they sort of, that was the first confirmation that we have this black body radiation that was predicted in the 1940s. And then in 1990 came the COBE satellite. It is the Cosmic Background Explorer satellite, which went and measured. This was a space telescope, because by that time the space technology has improved, and it is a space telescope. It went and measured the spectrum of the cosmic microwave background, and it has been the most perfectly measured black body spectrum in human history. Okay, so even in a lab, you do not have such a perfect black body. This black body distribution that we are seeing is the thermal state of the very, very early universe, when the universe was roughly 300,000 to 400,000 years old. And this black body has a temperature of 2.73 Kelvin. So Penzias and Wilson measured this temperature. It came out around 3 Kelvin. But then COBE, and there are some other ground-based also satellites, and of course later space-based satellites, which went and precisely measured this black body temperature to a very, very high precision, in fact, part in 100,000, and it roughly came as 2.73 Kelvin black body. And this black body peaks at about 1 millimeter. So if we apply Wien's displacement law, which says lambda T is equal to constant, so if you put T equal to 2.73 Kelvin, lambda roughly comes at 1 millimeter. and that's why this black body peaks at the microwave regime, and that's why we call it a cosmic microwave background. So it's a cosmic background radiation because it is the relic radiation of the Big Bang, and since it peaks in the microwave, we call it the cosmic microwave background. Okay, so this is Penzias and Wilson using this radio antenna, because this was 1960s, and in the 1940s we had the Second World War, and then the entire 1950s there was a lot of development on radio astronomy. So the development of radio astronomy was actually played a pivotal role in detecting the microwave background. And I will not get into the story. So sorry, these two scientists were given the Nobel Prize in Physics in 1978 for their discovery of the microwave background, and that was the first cosmology related Nobel Prize in Physics. So, Nobel Prize started long back, but the first cosmology related Nobel Prize was the discovery of the cosmic microwave background. Okay, so this is the original paper of Penzias and Wilson, and this is the title of their paper, because as I said that it was accidentally discovered, because these two people, Penzias and Wilson, they did not know anything about Big Bang theory, and they were looking for other things, other observations. They were in Bell Lab scientists, and they were looking for other things, but then suddenly they measured this signal. Suddenly they measured this signal of which they could not explain that what is the reason that they are getting this constant sort of signal in their this radio receiver. And then Bell Labs is very close to Princeton University, and then in Princeton University, Bob Dickey and his group, which include Jim Peebles, who got the Nobel Prize couple of years back for his huge contribution to cosmology. So Dickey and his students and postdocs, they were working on cosmology, and they were trying to understand Big Bang theory. They wanted to measure this black body radiation that was being predicted from the 40s. So these guys went and heard their seminar, and then they sort of thought that maybe what we detected is the relic radiation of the Big Bang. And that's why you can see that the title of the paper is A Measurement of Excess Antenna Temperature. They never spoke about Big Bang theory that much, and at the end they actually acknowledged Dickey and his people, because it was inspired by a discussion or a seminar that they attended in Princeton University. But it was an accidental discovery. Now we're going to talk that what is this microwave background. So for that, this is a slide, physics behind the CMB, but I'm going to just take a detour and do some board work to explain what this cosmic microwave background is. Okay, so now the issue is that so we are talking about the evolutionary history of the universe. Now the universe during Big Bang, this is like, infinitely hot, so it's very, very, very hot universe. But then, sorry, my spelling, I hope I wrote it correctly. So then this universe is gradually cooling. Okay, now it cools because when it is very hot, let's say we are talking about a very hot phase of the universe, then this hot phase of the universe, you do not have any neutral matter. Everything is in ionized state. We are not talking about the most hot phases of the universe. This is, let's say, many, many years. Let's say 1 million years after the Big Bang. Okay, so 10 to the 6 years after the Big Bang, or sorry, 300, not 10 to the 6, let's say 10 to the 4 years. 10,000 years after the Big Bang, the universe is very, very hot. Now, how hot it is exactly, that can actually be sort of found out by the temperature of the CMB. We call it, if T0 is the current temperature of the CMB, we can multiply this T0 with a factor. This is called the redshift of the universe, which is related to the age of the universe, and you can find out what will be the typical temperature of the universe. I'm saying temperature of the universe. That's not the right way to say. It's actually the temperature of the relativistic species of the universe. So let's not get into that technicalities. So let's understand the CMB from a very, very interesting bachelor's level physics that we learn in our physics classes. So what happens is the following, that before, let's say, before, when the universe is very hot, by hot I mean hotter than tens of electron volts, okay, tens of EV. Now you can convert EV to temperature by, so EV, and you have to divide by the Boltzmann constant, and that will give you the typical temperature. So we are talking about temperature that are greater than thousands of Kelvin. So let's say 10,000 Kelvin or 20,000 Kelvin is the temperature of the universe. Now everything stays in the plasma state. So if we imagine that the free electrons and the free protons, if the universe is very hot, that means the typical energy scale of the universe is high, then this electron and proton will stay in a plasma state. But when it gradually cools, you actually form neutral hydrogen, plus this is a photon, right? So there is a forward reaction which actually combines, where a proton combines with an electron and forms neutral hydrogen and photon. And then there is a backward reaction where this neutral hydrogen is photodisintegrated back to its constituents, which is the free electron and the free proton. Okay. Now, depending on what is the temperature of the universe, so if we now go to an energy scale, by temperature I mean energy, because we just have the Boltzmann factor there. So let's say when we reach an energy scale of 13.6 eV in the universe, this is a very special energy scale in atomic physics, because this is the ground state. If you have studied Bohr theory, this is the ground state of hydrogen, or this is the ionization energy of the hydrogen atom. So now, when the universe, when the temperature scale of the universe goes below the ionization energy of the hydrogen, what happens is you typically start making more and more neutral hydrogen. Okay, there are a lot of complexity in it. I'm not getting into the details. Now, this is the reaction that we are interested in. So the universe is gradually transforming from an ionized state to a neutral state, and we are having pockets of neutral hydrogen formed in the universe. Now, you have to, because the universe just doesn't have electron and proton. It has photons, it has neutrinos, it has everything, right? It has lots of things, lots of other particles. So in the context of early universe, we have a concept which is thermal equilibrium, that we already have the concept. We always talk about thermal equilibrium, which we learn in school, in high school, in our physics classes in high school. But here, there is an issue. It is a thermal equilibrium in an expanding background. Okay? Because, why? Because the background, the universe itself, so this universe have all these microscopic particles, and they are interacting with each other, and there is a temperature scale that we can define of the universe, but this background itself is expanding. Okay, so that means the temperature scale is constantly falling. So in this context, how do we approach the concept of thermal equilibrium? And so we say that there is a scattering rate. So let's say if I think about this reaction has a rate of scattering rate, not this reaction, sorry. So let's say if I have free electron and then there are photons, right? So this is matter, this is radiation. Now it turns out, as long as there are lots of free electrons in the universe, the photons and electrons can get scattered to each other, and we say that matter and radiation are tightly coupled. Okay, that means the radiation is coupled to matter, and so the radiation is not free, right? There is a constant reaction, constant scattering. Actually, this is Thomson scattering, a constant Thomson scattering going on between the electron and the photon. Now, once we start forming neutral hydrogen, that means we have less and less number of free electrons, the scattering rate, the Thomson scattering rate actually decreases. Okay. So once we have lots of free electrons, then as I said, that the electrons and the photons or matter and radiation are in thermal equilibrium. So, but then the universe temperature gradually drops, we form neutral hydrogen, and this Thomson scattering rate drops as the universe expands. But then, as I said, that we are talking about an expanding background. So there is another scale. This is called the Hubble scale. This Hubble scale is actually, this has a dimension of inverse time. So 1 by h gives you some Hubble time, a typical time scale. So this is related to the expansion rate of the universe. So now we have two rates in the universe. One is gamma and one is h. This is the microscopic scattering rate and this is the macroscopic expansion rate. So there are two time scales, 1 by gamma. So this is the typical scattering time scale between the electron and the photon. How many what is the typical time scale of scatterings? The scattering is a statistical process, and 1 by h is a Hubble time scale or an expansion time scale. Now, not for just this issue, but what happens is that when 1 by gamma, that means the scattering time scale is much less than 1 by h, we call there is thermal equilibrium. Okay, that means we have many scattering events within the expansion phase of the universe. When 1 by gamma is of the order of 1 by h, we call it sort of decoupling. That means now the scattering time scale and the expansion time scale are becoming comparable to each other. That means the number of scatterings are not that much. It's getting down. That means the previously when the electron and photon were in thermal equilibrium, now the photon and the electron are out of equilibrium. Okay, that's called decoupling. And then when 1 by gamma becomes much greater than 1 by h, that means there is hardly any scattering event going on. This is called free streaming. So what happens is, once the universe becomes more and more neutral, the free electrons vanish from the universe. And as you know, that photon can only interact with charged particles. So if the universe is fully neutral, the photon scattering rate with matter gradually decreases, and at the point when it decreases so much that now the photons do not scatter at all in the universe, and it free streams in the universe. And that is the origin of the microwave background. So it's a thermalized radiation which went out of equilibrium completely, and it stopped doing any interaction, and it just free streamed to today's, unless we detect them in our detector today, right? So that's why the epoch of the CMB is called surface of loss scattering. Okay, so that's the origin of the universe, origin of the CMB. So and this happened, one can do detailed calculation, which we will not do today. This happened at a stage when the universe was roughly 300,000 to 400,000 years old. Also, it's something, this Z, this is called the redshift. Redshift is actually a scale of time, because astronomers use this because they look at photons. And so this is around redshift of 1100. And today it is redshift of 0. So higher redshift means back in time. So once the photons free stream and they have a thermal distribution, what happens is that the black body, this was a black body during last scattering, and then this black body just stays a black body as the universe expands, except the peak temperature of the black body goes down because the universe is expanding, so the peak temperature is getting different. Okay, at this time the peak was at the optical energy scale, and now we detect the peak at the microwave scale. So I hope sort of I made sense what I mean by the origin of the CMB. Okay, so universe was filled with a plasma of baryons and photons. By baryons, I mean protons, and they were tightly coupled by Thomson scattering. And then universe at the ionization temperature of the hydrogen, you form neutral atoms start forming. That is called the epoch of recombination, because the electron and protons are combining. So there are shortage of free electrons, and then the Thomson scattering rates goes down, and photons free stream to today's CMB sky. And that's why the epoch of this recombination and decoupling is called the surface of, not large, sorry, it is the last scattering, because that's the last time the photons interacted with matter, which is not completely true, we'll see. So now, what the COBE satellite measured, we saw this black body spectrum. So this is the physics behind the CMB, and you see that it's a very, very perfect black body. So the predictions of Big Bang theory were strongly confirmed once this black body was detected so precisely and over this large frequency range or wavelength range. Okay, and the predictions matched very much with the theory, and we found out that the temperature of the black body is 2.73 Kelvin. Okay, so now the fantastic thing about the CMB is that this is, as we discussed, are the photons that are coming from Big Bang, and these are the photons that last time scattered with matter only at redshift of 1100 or 300,000 years after the Big Bang. So that means these photons carry unaltered information of the very early universe. So this is great that now we have it too, and the other fun thing is that before the epoch of the CMB, the radiation was tightly coupled, so the universe was opaque. But this is the first time the universe got transparent. So we now have the ability to see the universe or to learn about the universe when it was very old through our fantastic electromagnetic signals. In this case, we have to look in the microwaves. So that's the joy of the CMB. And this is very dear to my heart because my thesis was involved in some anisotropies in the CMB. Now, what is this? So next the topic, because I said that anisotropies in the cosmic microwave background. So these are photons, and this is a black body photon, and we saw that the black body has a temperature, and then of course these are photons, so these photons have polarizations. There are other issues. Now, we will only discuss temperature fluctuations. Now, what we mean by this temperature fluctuation? So we just saw that we measured the temperature of the black body to be 2.73 Kelvin. To be precise, I think it's 2.7215 plus minus 0.00001, something like that. So it's precise up to part in 100,000. But what the COBE satellite, in addition to measuring the spectrum, what the COBE satellite did is it took a map. So it is an all sky survey. So it looked at the sky in these frequencies, okay? And it has a very precise instrument which could measure the deviation from the black body or the temperature difference from the black body at part in 100,000. So what do I mean by that? Let me again escape the stop sharing, and let me just go to the board. So this is what I exactly mean, that we have the all sky, okay, and we know that from all over the sky, so the black body that I was talking about is very homogeneous and very isotropic. So it's very, very, very close to 2.73 Kelvin black body, and it's same if you look at different directions of the sky. But then what COBE did is it measured, so it's essentially a flux versus frequency or wavelength measurement. So it measured very precisely the frequency and made a map of the CMB. So essentially this map is very homogeneous because it's a 2.73 Kelvin black body. But then if you tune your detector such that the difference between 2.73 So it's a difference in part in 100,000. So suppose one place is 2.73121 Kelvin and the other is 2.73120 Kelvin. So it's a 1 in 1 in 100,000 difference. If this temperature difference can be measured by the detector, so if we can design a detector that's that close that it can measure these very precise difference in temperature, and that's what Kobe had as one of his detector. It's the it's the I think the DMR, Kobe DMR. So then it saw an amazing thing that no, if I look at different parts of the sky, not every part has a 2.73121 Kelvin black body. Sometimes it's 2.73120, sometimes it's less than that, more than that. So there is an anisotropy in the temperature. This is delta T over T naught, where T naught is 2.73 Kelvin of the order of part in 100,000. So you can imagine that no, it's not the homogeneous and completely isotropic and completely high homogeneous distribution of black body. It's very homogeneous and isotropic to a large degree, but then there are these small fluctuations in its temperature. Okay, so that was a phenomenal discovery from the Kobe satellite that came in the 1990s. And again, the Kobe team was given the Nobel Prize for first detecting precisely this black body, and second for making this map and finding the temperature anisotropy, detecting the temperature anisotropy. Okay, so this was the Nobel Prize was given in 2006, and that was the second cosmology related Nobel Prize. Now, the point is that when you talk about telescopes, this is a space telescope, we talk about angular resolution. So that means when 2 points in the sky, how well can it resolve? And Kobe had an angular resolution of 7 degrees, so it could resolve. These are the blue and red are hot and cold spots. When I say hot and cold spot, I mean that it is higher than the mean temperature or it's lower than the mean temperature. But this high and low is very small. It's very small, part in 10 to the minus 5, roughly. The average high and low is part in 10 to the minus 5. So green, blue and red are essentially the difference from the mean. Sometimes the difference can be positive, sometimes the difference can be negative. And that's why we call them hot and cold spots. Okay. So now Kobe had an angular resolution of 7 degrees. Then came the WMAP satellite, which had an angular resolution of 30 arc minutes. And we had a very precise measurement of this temperature fluctuation. And then the latest one, this is the Planck Surveyor satellite. This has an angular resolution of 5 arc minutes. And you can see what Kobe crudely measured the temperature fluctuations. Planck measured them very precisely, and you can see the red and blue spots. Again, they are cold and hot spots. By cold and hot, I explained what I mean by cold and hot. That is the difference from the mean of these temperature fluctuations in the sky. So now comes the question that why do we see these temperature fluctuations? Okay, what is the source of this temperature fluctuations? We just discussed that we expect a very thermal distribution, and we detected that this is a very thermal black body distribution because it tells us about the thermodynamic state of the early universe, which is a thermal distribution of the photons. We're looking at the photons, but then we see that these photons are not fully a black body, but there are fluctuations in their temperature in different parts of the sky. So then comes the question that what is the origin of these fluctuations? Okay, so that's the most this is also very attractive part. So again, I will just okay, let's do that. Now, when we look at these temperature fluctuations, we generally divide them into two main categories. One is called the primary anisotropy. I think there is a question probably. Somebody wrote in the chat box, Anudeep Chibukula, is 2.7 Kelvin the temperature of the free streaming electrons or of any other matter after 300,000 years of Big Bang or of space-time itself? So Anudeep, it's actually the temperature of the free streaming, not the electrons. It's the temperature of the photons. We are talking about the free streaming photons because the electrons, they combine with the protons. So they are not free. We don't have, yes, later also free electrons are formed, but the electrons combine with the protons to form neutral hydrogen. So at that epoch, there are no free electrons in the universe. But the photons, which was otherwise constantly getting scattered by the electrons, are now free because there are no free electrons in the universe. So it's a charge neutral, and we know that radiation, they only interact with charged particles, but if it's all neutral, then this radiation doesn't have anybody to interact with, and that free stream. So it's the temperature of the photons. Did I make myself clear, Anudeep? If that is fine with you? Is that okay? Okay, I hope it's that okay. Thank you for asking. So now we are okay. So now we are talking about this temperature fluctuations, and as I said, that we broadly classify them into two categories. One is called the primary anisotropy in the cosmic microwave background, primary temperature anisotropy. We're only talking about temperature anisotropies. And the other is called secondary anisotropies. What's the difference? The difference is that when what we symbolize or what we call primary anisotropy actually happened during the epoch of last scattering. So these are the physics that went in making those anisotropies in the very early phase of the universe are called primary anisotropy. And the reasons for which we have fluctuations, temperature fluctuations in the cosmic microwave background in the late, because the CMB is free streaming, the microwave, the photons are free streaming, but yes, the universe became neutral and the photons got free. But then, if you remember that picture, if we remember that picture, so yes, this one. So the photons got free from this epoch. This is the microwave background. These are the hot and cold spots, and it's freely streaming in the universe. But then, as it free streams, there is also structure formation going in the universe. So there are stars forming, there are black holes forming, there are galaxies forming, so on and so forth. Okay. So now these photons are likely to interact with the matter in the late universe, and as a result of that, there are fluctuations, temperature fluctuations that we see in the microwave background, and those are called secondary fluctuations in the cosmic microwave background. Now, what is this primary? What are the source of this primary anisotropy in the CMB? I will not get into the details because this itself is a 1 month course probably. So the first thing that causes temperature fluctuations is the fluctuation in the gravitational potential. So what do I mean by that? This is what I mean. So let me again share this board and explain what I mean by that. So now what happens is, so we are talking about electrons and photon. Okay. Now these are all standard model particles. Okay. These are particles that we understand through the standard model of particle physics. Now, some of you definitely know or might have heard during the summer school or the refresher course that we have something called dark matter in the universe. Okay. Now, this dark matter has no electromagnetic interaction. That means radiation doesn't couple with dark matter. But this dark matter has gravity. Okay. And it turns out that the dominant form of matter in the universe is this dark matter and not the standard model particles. Okay. So we are talking about baryon photon or standard electron photon interaction. and there are other standard model particles. But then there are also dark matter particles in the universe, and then this dark matter can clump. So their gravity is Newtonian gravity or general relativity. Newtonian gravity is big brother, general relativity. So gravitationally, they act similarly to normal matter, but electromagnetically, they act differently to normal matter. Okay. So what happens is that the plasma I am talking about, these electron, proton going into hydrogen and photon, all this business is happening in a background of dark matter clumps, and these things are feeling the gravity of dark matter. Okay. And as I said, that so the gravity is also, the dark matter also feels the gravity of this, but this is, since there are more dark matter, it's more, much more, 90% roughly is dark matter, and then the 10% of matter. The universe contains radiation, matter, and then this the dark energy that we discussed. But among the matter component of the universe, the majority, the lion's share is from the dark matter. So what happens is they can feel these photons, as you know, some of you might know, through Einstein's general relativity, although the photon is massless, but through GR we know that the photon can feel the gravitational field produced by matter. Okay. So what happens is that this entire thing, this entire reaction and all that stuff is happening in a background gravity of dark matter. And if I denote rho dm as the density of dark matter, okay, then what I can say is, if I just look at Newtonian gravity, and this is weak field gravity we are talking about. So Newtonian is a fine picture. If we go to strong fields, we have to take general relativity. But here, what we can do is, some of you are definitely familiar with the Poisson's equation. If you are not familiar with the Poisson's equation, don't worry about that. This is the gravitational field, and this is the matter. Now, in this case, it will be dark matter. So, we will have a gravitational potential or field that will be produced by the dark matter. Now, if this dark matter is completely uniform, then we have a uniform gravitational field. But if there is distribution, there is fluctuations in the density of dark matter in the universe, so I have rho plus delta rho, then I have phi plus delta phi. So I have, due to density perturbation, this we called density fluctuations or density perturbation. So due to the density fluctuations in the dark matter, there can be also density fluctuations in the normal matter. Due to these density fluctuations, we will have an inhomogeneous gravitational field. And in this inhomogeneous gravitational field, when these photons travel, they will also incorporate some temperature change. And this is called the Sac Souls Effect, where delta T over T naught, that means we have a black body distribution of photon. Let's say they have a temperature of T naught, but this will be proportional to 1/3 delta rho over rho. I think I'm right. Yeah. Yes, I think this is the right expression. So so that means the fluctuations in the temperature of the photons will be related to the fluctuations in the gravitational field due to the inhomogeneous distribution of matter in the universe. This is completely gravitational. This coupling that we are talking about is electromagnetic coupling, because you have charged particles combining and forming neutral hydrogen, but this is coming from gravity. Okay, but that's great. So now let's go again to the slides. Share, say. So fluctuations in the gravitational potential causes an isotropy in the temperature via something called the Sac Souls Effect. This is the Sac Souls Effect because Sachs and Wolf in the 1960s first predicted that if a photon moves in an inhomogeneous, if a distribution of photon moves in an inhomogeneous gravitational field, then this photon will have an inhomogeneous distribution of energy, and that in this case will be manifested as a temperature anisotropy. Now, the other thing that happens is that we have this coupled radiation and matter, right? And then this radiation and matter is under gravity. So what gravity would want is it will want to collapse matter and radiation. We are talking about this tightly coupled electrons and photons, let's say. So if under gravity, it will try, this is a plasma consisting of photons and electrons, and gravity will try to compress it because that's the nature of gravity. It's going to compress. But then radiation has radiation pressure, so pressure will try to resist gravity. And as a result of that, there is an interplay between pressure and gravity. And as a result of that, we will see something called acoustic oscillations. Okay, so this is sound waves will be generated in the universe because we are talking about propagation of fluid perturbations, that is sound waves. So we'll have sound waves in the universe, and this compression and rarefaction will happen. This is a beautiful physics, and that will incorporate additional temperature anisotropy in the microwave background photons, in the background photons. And then there is something called Doppler Shift, that if we're looking at the photons from our reference frame, if it's moving away from us, there will be a red shift. If it's moving toward us, there will be a blue shift in its energy or temperature. Okay, so this is the source of the primary anisotropy that happened in the early universe. Now, how much time do I have? So I'll have to wrap up quickly. Now, this anisotropy, as we said that Kobe measured it, precisely measured by the WMAP satellite, we'll come to that. And from these, as you saw in the map, let's go to this map. So you can see that we have an all-sky map of the temperature fluctuations, and we have a very rich physics that is responsible for the temperature fluctuations. So now, utilizing the statistics of these temperature fluctuations, will come in a minute, we can learn a lot about the content and the evolution of the universe. Okay, but before that, let me explain what the secondary anisotropies, as we said, that this is the fluctuations in the temperature that occur due to its interaction with matter in the late universe. Because when structures are forming, I say dominant in much smaller scales, it will be clear what I mean by that. And this is the least of the secondary effect that we see in the microwave background. I have particularly marked in red the Sunyaev-Zel'dovich effect on which I work. So if I get time, I'll briefly describe the Sunyaev-Zel'dovich effect. But there are a number of effects that are creating these secondary fluctuations in the anisotropy. Now, I just talked about this statistical property, right? This is an all-sky map. So the methodology or the formalism, this is delta t over t theta phi, because we are talking about the surface of the sky. So essentially, it is approximated as a surface of a sphere, and on the surface of a sphere, we can expand any function in the spherical harmonics, and then from there, we can find the temperature correlation between point 1 and point 2 is a function of theta. That means angular separation in the sky. And then we can actually find out that how the temperature fluctuations using this formalism varies as a function of angular scale. Now, this L is called multipole moment. If some of you have studied quantum mechanics or in your electrodynamics courses in your first year or second year, you have studied multipole expansion of a radiation field or of an electric field or a potential, electric potential or magnetic potential. So this is essentially that. And this L is a multipole moment. So what this L and theta are related. So theta is inverse of L. So this is actually the angular Fourier transform. Theta is in real space and L is in Fourier space, angular Fourier space. Okay. So essentially, I write this delta t as L into L plus 1 twice pi CL to the half expectation t. This is the mean temperature. So essentially, delta t over t is given by this, and this is called the power spectrum of temperature fluctuations, which tells us what is the temperature anisotropy at different angular scales. And this is an old plot I'm very sorry for that. I should have a revised plot, the most recent ones from the Planck satellite particularly. But I particularly like this plot because this was one of the first detections. This is very near to my heart. So here I am plotting. L is our multiple moment. So that means if I increase L, I'm decreasing the angular separation, sky separation. That means this is small angle fluctuations. This is large angle fluctuations. And these are that L into L plus 1 here twice pi in microkelvin square. Now, fluctuation can be both positive and negative. But when we calculate the power spectrum, we just only take the square of it. That means both positive and negative becomes positive. Otherwise, there is some issue. So we take the square of temperature fluctuations. Okay. And what you can see is these are the data points from the WMAP 7-year map. This is ACBAR, some ground-based telescope. Quad is a ground-based telescope. ACT and SPT, they were just coming online, just came the first data. And the reason I show this plot is because I was involved with the ACT team for the Sunaev-Zeldovich business. And since we saw this data, it's so dear to my heart that I'm showing you a 12-year-old plot. Sorry about that. It has improved a lot. But this plot is interesting in the sense that what you see here in the red solid line is a theoretical fit to the data. And what you see is that here there is a flat part. Here you have like oscillatory changes in the temperature fluctuations. And then it falls off and then it again increases. Okay. And here is the fit. This red line is a theoretical fit. And these fluctuations, mostly for lower values of L, are the primary fluctuations. And by fitting this data, you can see that this is a very complicated graph, right? These are the acoustic oscillations we are talking about. And this is the Sac Souls plateau, and then it falls down exponentially. The temperature fluctuations are suppressed for reasons we can discuss if somebody has a question. But again, the temperature fluctuations after certain scale increases. And this increase is mainly due to the secondary fluctuations, that is, interaction of CMB with matter in the late universe. And majority of this temperature fluctuation actually comes from the Sunaev-Zeldovich effect that I was talking about. Okay. So let me just give one example of how you can, let me see how much time do I have. Okay, I have still 8 more minutes. Very good. That's very good. So let's see. So as I said that if I look at these fluctuations, the statistics of temperature fluctuation, and we are fitting this model is a very, very complicated model. As you can see that it have to fit lot of features. It have to fit the peaks, the troughs, the flat part, the exponential fall. That means this model has lots of features that are related to the content and evolution and the geometry, etc. of the universe. So I'll give you one example that what can we learn from the power spectrum of temperature fluctuations. And this is CMB and the curvature of the universe. Now, those of you who are familiar with general relativity know about the curvature of space-time, and universe can be, so it also applies to the universe. The universe can be positively curved, can be negatively curved, can be flat. Now, what has that to do with the temperature fluctuations? The reason the geometry of the universe plays role is here because we have the surface of last scattering from which the CMB photons are free streaming to us. Okay. Now it has to pass through the entire universe, and there is something called gravitational lensing. That means the photons will follow the geometry of space-time. Okay. So here, this is an example. This is a lens example. So suppose the universe is positively curved. Okay. So suppose here is a length, here is a stick, or here is some structure that I am seeing. So if it is positively curved, then it's going to converge in this way. And what the observer will see, so this is the original length, or let's say in our language, this is the original angular separation between the hot and cold spots that we see in the CMB, because you are measuring it in the sky, right? Now, but these temperature fluctuations are coming from the surface of last scattering. In fact, this is the size of the sound horizon. Let's not worry about that. So suppose this is a scale and the universe is, so this is coming from last scattering and it's a positively curved. So if it's positively curved, you are going to see a higher length scale, okay, or higher angular scale. If it is flat, you're going to see exactly what it is. If it is negatively curved, then the light will come in this way. And if it is just what you learned in your optics courses in high school, lenses, so you're going to see like concave and convex lenses, you're going to see a small length scale or small angular scale. What does that mean? Imply when we are looking at the temperature fluctuations? It implies that if universe is closed means positively curved. Forget about why I call closed and open. It's actually related to the geometry of the universe. So if it's positively curved, hotspots appear larger than actual size. If universe is flat, hotspot appears according to its actual size. If universe is open, that means negatively curved, hotspots appear smaller than actual size. Now smaller means smaller theta, larger means larger theta, and larger theta means small multiple moment, small l, and here small theta means large L. Okay, so now you can see that this position of the first peak, this is a very, very important thing that one can work out from theory using density perturbation theory and all these physics. This is a very, very rich physics. And the fact that this first peak occurs at roughly L equal to 200, in fact 180, yeah, about 200. The fact this is a log scale, so 100, this is 200. So the first peak appears at L equal to 200, and then one can do theoretical model and show that the fact that the first peak appears at L equal to 200 strongly tells us that the universe is flat. If it was not flat, if it was positively curved, then the size would have been bigger, so it would have been appeared at L, which is less than 200. If it was negatively curved, it would have appeared at an L that is higher than 200. So this essentially, there's a very, very precise measurement of the first peak, first from the WMAP satellite, and then of course from the Planck satellite and some other experiments strongly confirmed that the current geometry of the universe, not current, the geometry of the universe is very flat. Okay, and there are theory which explains that why the universe has to be flat, because general relativity doesn't prefers one over other. It could have been positively curved, it could have been negatively curved, it could have been anything, but it appears that our universe is very flat. So that's one thing that you can learn from the CMP. Now I'll just quickly end my talk with the Snav-Zeldovich effect, that is the leading secondary effect. The fact that I'm talking about is because I work on it. So what happens is the following. So we said that there's a surface of loss scattering, which means that these electrons, these photons free streamed and they never scattered with anything. But then later we said that there is structure formation in the universe. We form stars and galaxies and everything. So these photons actually interact with matter, and that is the source of the secondary fluctuation. So, and one of these is the Sunyaev-Zeldovich effect. So what happens there? So suppose we have the surface of loss scattering. That means the photons are free streaming. They are free streaming. Now, this is us. Let's say our observer. This is our telescope, whatever. So now, suppose in our line of sight, so this is us and this is the surface of early universe surface of loss scattering, and this is all sky. So in our line of sight, if there is a galaxy cluster, now galaxy cluster is a bound, this is the largest visualized object in the universe. It is a conglomeration of many galaxies. Okay, so these galaxy clusters have a huge gravitational potential, and it turns out that there is a lot of X-ray gas. So it's very energetic place, and as a result, there is a huge plasma of free electrons. Now imagine the photons can interact with these electrons. Now this is low energy photons because we are talking about relatively nearby universe. These clusters are at a much later stage after last scattering. So here the photons have redshifted and their energy is low, whereas the clusters have electrons which have keV, X-ray energies. So these electrons are high energy and the photons are low energy. And now these photons can again Compton scatter or Thomson scatter, Compton scatter with these free electrons. And as a result of that, there is a transfer of energy of these photons. Okay, so some of these photons gain energy because there's a scattering process. This is a relativistic energy momentum conservation problem. So this is a distribution of photons. This is a black body distribution. And then in a cluster, there is a Boltzmann distribution of electrons. This is a thermal classical gas, classical electron gas model, if you have learned in your StatMech courses. So now you have to find out that these photons will gain energy, all the photons. And as a result of that, suppose these photons now have a black body distribution that we discussed. Now all of them gain energy. Okay, so you can see that all the photons shifted to the lower wavelength. Okay, this is lower wavelength or higher frequency. X is this normalized frequency. But the gain, it turns out, if you do the relativistic calculation, it turns out that the gain of energy is not uniform for all photons. Rather, it depends on the initial frequency of the photons. As you know, in a black body distribution, you have photons of all wavelengths. So now this transfer of energy depends on the wavelength, and as a result of that, there is a shift in the spectrum of the microwave background, and it's no more a black body. So you can see that this dashed line is a shift, and what happens is that there is a crossover between the solid and the dashed line. So at this crossover frequency, this is called the null frequency, the flux of the shifted distribution is exactly same as the black body. Below this frequency or below this wavelength, the dashed line is below the solid line, and above this, the dashed line is above the solid line. And that means the flux is lower here, the flux is higher here, and that comes as hot and cold spot in the CMB. And this is called the thermal Sunyaev-Zel'dovich effect. And then there is something called the kinetic Sunyaev-Zel'dovich effect, which is essentially that the cluster has a motion because although it's a gravitationally bound object, it still has gravitational effects with its surrounding. So this cluster, any gravitationally large volume we are talking about the universe will have some velocity, call it peculiar velocity. So as a result of this velocity of the cluster, the photons will have a net Doppler shift in their spectrum, and that's called the kinetic SZ. So this thermal SZ is appearing because of the hot electrons in the cluster, and the kinetic SZ happens because of the bulk motion of the cluster. Now, current day cosmology in the last 10-15 years, lot has been done in the SZ effect, and as I said, that this peak is coming from the cluster Sunyaev-Zel'dovich effect. There are Sunyaev-Zel'dovich effect from other astrophysical objects. For example, my work involves Sunyaev-Zel'dovich effect from active galactic nuclei. And current state of cosmology or cosmic microwave background experiments is actually to detect these temperature fluctuations due to the secondary effect and learn about the evolutionary phase of the late universe. We have learned so much about the early universe. Now we want to understand the astrophysics of the late universe, and that's where we stand at the CMB science. Okay, so thank you very much. I will stop here, and now time for questions. If you have questions, sorry, I took 4 minutes long, and I should have ended probably 10 minutes back, but I'm just taking the leisure of since the next talk starts at 11:30. So please raise your hand or unmute yourself and ask questions if you have any. Okay, please.
Thank you very much, Suchitana. So, do you see any questions on chat?
I do not see any questions on the chat. There was one question which I answered previously, but if there are other questions, please feel free to raise your hand. You can ask the questions in English or Hindi or Bengali. These are the three languages I understand. I will try to answer them in the most convenient way. So if there is
Excuse me,
any,
ma'am.
yes, please.
Ma'am, I am Devesh. Ma'am, am I audible?
Yes. Thank you. Yes, please.
Ma'am, I want to understand. Ma'am, would you please elaborate what is the meaning of this flatness of the universe? Ma'am, I
Of the
think,
flat.
ma'am, it is not traditional.
So flatness of the universe is the spatial flatness. Okay. So if you think of general relativity, let's say we are talking about the solar system. Okay. So there is another question, Akshat Patrikar. I'll get back to you. So suppose we are talking about the solar system. Now we have the sun, right? And we know that the planets are orbiting the sun. That we can understand from Newtonian gravity. Now, if you look at general relativity, then what general relativity tells is that if you have matter, then this matter curves space time. So essentially, the mass is related. So mass is defined in general relativity as a property that curves the space time around it. So the sun's mass actually curves the space time around it, and in that curved space time we have the motion of the planets. Okay, so essentially it's the curvature of space. Now when you're talking in terms of the universe has matter and radiation and all the stuff that we know about, so it's expected that there will be a curvature according to general relativity. It turns out that the for reasons we can talk later, somehow the measured curvature of the universe. Now, how do you measure the curvature of the universe? You can measure a local curvature mathematically, that we understand. And we're talking about the global curvature of the universe. This is global curvature. How do you measure it? You actually don't measure the curvature. You write down the general relativistic equations, or you can actually have a Newtonian approach. You can write down the Friedman equations, and the curvature term comes there. And then through other observations, you can constrain the curvature of the universe. As I showed in the case of CMB, just look at the distribution of the temperature, hot and cold spots. And so from this is just not CMB, but from many other experiments, the curvature has not been directly measured, but the curvature has been constrained to be spatially flat. Did I make sense?
Thank you, ma'am.
Thank you. So I have a question from Akshat Patrika. Can you unmute yourself and ask the question? And then there is a question. Yes, please.
Hello, and thank you for this wonderful talk. Well, my question is that how do we actually figure out the actual size of hotspots in the CMB?
Okay, so that's a good question. So when I say the size, I don't mean how big the hotspot is. We look at the correlation function. Let's go to that slide. So let's go. Sorry. So let's go. Yeah. So if I go to this slide, so you see that we are talking about the angular scale of the sky, right? So it's like so 2 points in the sky, like let's say 2 hot spots in the sky, not really the, yes, we also care about the sizes of the hot and cold spots, and there are physics related to that, but let's say we are identifying 2 spots in the sky, 2 hot spots in the sky, and then let's say we have a separation between them, angular separation, let's say theta. Now what we do is we measure all possible pairs of hot spots which are separated by angle theta, and then we take the average fluctuation, that what is the average difference, or not hot spots, hot cold spots, whatever it can be, it's just the temperature difference. So when I say size of hot and cold spots, I essentially mean this angular separation between hot and cold spots. Did I make sense?
Yes, ma'am.
Okay, thank you.
Ma'am, I also have one more question.
So can we have the other questions, and then if there is time, we can take yours? Because
Yes,
I
sure,
see
ma'am.
somebody, Sneha Singh, typing a question. Can you talk about the monopole and dipole spectrum data? How do we get this? Okay, that's great, Sneha. So monopole is the monopole, that is the uniform temperature data. So that is means when we look at the sky, there is no difference, right? This is just a flat 2.73 Kelvin black body. The dipole, this is a very important point you took about. So the dipole, because if I talk, we are talking about the multipole expansion. So now the fluctuations in the CMB can occur for all the causes, from the primary fluctuations for the secondary fluctuations. But the dipole also occurs because the CMB photons. So now when it reaches to a detector or reaches to a telescope, let me now switch on the video. So when it reaches to a telescope, what happens is that it also comes through the local reference. So you have the local group, right? The Earth, the solar system, the Milky Way galaxy, and stuff. So this is the local group. Now there also there is a peculiar velocity, and due to this peculiar velocity, there is a Doppler shift of the spectrum, and we actually see half of the sky being hotter and half of the sky being cooler. This is just pure Doppler shift. So this is red shift and blue shift. And that is the dominant dipole term. So if you can measure that anisotropy between two halves of the sky, that's the dipole anisotropy. From there, you can put constraint on sort of what the peculiar velocity is with reference to the CMB rest frame. Sneha, did I make sense? Thank you. So there is a question hand raised by Shlok Shah. Shlok, please, sir.
Hello, ma'am. Am I audible?
Yes, absolutely.
Actually, ma'am, I had more of a general question.
Yes, please.
You mentioned that the decoupling occurred between 300,000 to 400,000 years. And similarly, we have also other epochs in cosmology.
That's right.
How are these scales, like this particular value, calculated?
It's a very good question.
Is it like the speculation or?
No, absolutely not speculation. So, so it turns out that we are talking about the decoupling of photons from matter, right? So what we do is, so suppose when the equation that I wrote, that you have E plus P going to H and gamma, that means there is this recombination. So we can actually use, first we can just use equilibrium statistical mechanics, and this is classical statistics. This is classical statistics. So the formalism is the Saha equation. I did not do it, but you can look up in cosmology books. So using the Saha equation, which is actually the equilibrium abundance, but then there is also decoupling. So there is out of equilibrium science involved. But let's say we have to first order, if we do equilibrium statistical mechanics and use the Saha equation, then you can find out what is the ionization history of the universe. Okay, so how over time the universe goes from a completely ionized phase to a completely neutral phase. Okay, that you can exactly do the calculations. Now there are three parameters that you can constrain with observations, and it turns out that by the time the age of the universe is roughly 400,000 years, the universe, a large part of the universe, has become neutral, and we see the photons decoupling. So this comes from very precise measurements. Did it make sense, Shlok?
Yes, ma'am. Thank you so much.
Yeah, and all these calculations are not like speculation. There are very strong physics that tells you that what should be the energy scale when all of these occurs. And from there, if you measure very precisely the temperature of the microwave background, you can extrapolate that at what age of the universe would you get the energy scale which is responsible for the physics that we're talking about.
Yes. Thank you so much, ma'am.
Thank you. So are there other questions? If not, we can go to the second questions of Akshat. Are there other questions? Okay, if not, Akshat, can you, maybe that's the last question we can take. Akshat, your second question, please.
Yes, ma'am. Ma'am, my second question is that, ma'am, previously I had read in an article that the curvature of the universe was actually, It was also measured with one of the ways in which they measured the sum of all the angles of a triangle on the CMB. And can you
Yes.
please elaborate a little more about that?
Okay, so that's okay. So I only talked about line, right? So if we go to that slide, I know what you mean. Just one sec. So if we go to the slide, so when we are talking about theta, that means we are talking about the angular separation, right? The angular separation. That means this is like a line. This is 1 point. This is 1 point. But you are talking about triangles, so that this is called the 2-point correlation function, because we are measuring the temperature fluctuations between 2 points on the sky. Now, when you have a triangle, that's a 3-point correlation function. And yes, using the 3-point correlation function, you also have additional constraints on the geometry. You can have 4-point correlation function, which is like 4 points. This is a square. So this is called going to the higher order moments. You can have more and more constraints, not just of the geometry, both the geometry and the content of the universe. Did that make sense, Sakshat? Did I answer your question?
Yeah. Yes, ma'am. Yes.
Thank you so much.
Thank you.
Okay. I think there are no more questions. So I really again like to thank everybody who was patient enough to hear my talk. Unfortunately, this has to be done in online mode. It would have been nicer if we do it in offline mode. And many thanks to Professor Debarati Chatterjee for organizing and giving me the opportunity to speak to the audience. And thanks to IUCAA
Thank you very much
for organizing this program and making it so vibrant and exciting.
Thank you very much
Thank you
for
very
joining
much.
us and for patiently taking all